Today I would like to talk about torque in equilibrium. What's mean by torque? Torque is a rotational equivalence of force. So, a net torque will cause an object to rotate with an angular acceleration. Because all rotational motion have an axis of rotation, a torque must be defined about a rotational axis. A torque is a force applied to a point on an object about the axis of rotation. The size of torque depends on two conditions. The first condition is the size of the force applied, and the second is its perpendicular distance from the axis of rotation, which depends both on the direction of the force plus its physical distance from the axis of torque, either positive or negative. It will be positive when the turning tendency of the force is anti-clockwise, and it will negative when the turning tendency of the force is clockwise. The direction of a torque is determined by the direction of rotation of torque will cause an object to adopt. Torque is a vector with magnitude. The equation of torque is T equals Rf sin theta, where theta is the angle between R and F. R is the distance between the rotation axis and the point of application of force. SI unit for torque is Newton meter.
This video is on torque and equilibrium. Now, torque is a turning force, and this is crucial to understand for the rest of this video. If we're thinking about what a turning force is compared to a regular force, imagine you're trying to undo a bolt with a spanner. If the bolt is really hard to get undone, there's two things you can do to make it easier. The first thing you can do is just push down a little bit harder. The harder you push down, the more likely it is that the bolt is going to turn. But failing this, you can also just go and get a bigger spanner, one that's longer, and push down the very end. These are two ways you can increase your turning force, and both of them will help get the bolt undone. So that relates to torque. The force, how hard you push down on, and the distance, how far away from this bolt or the turning point you actually push down on. So it's force and distance that lead us to the formula for torque, which is that torque, this little Tor symbol here, equals force multiplied by distance. And often the force that we look to use is found using the formula F equals ma, or more often with weight forces, F equals mg. So now that we kind of have an idea of what torque is, it's a turning force, let's look at what equilibrium is. Now, equilibrium means that an object is completely stationary. So it means that there's no rotation at all and there's no acceleration at all. So for example, this bench here, or this plank of wood supported by two blocks, it's not moving at all. It's not rotating anywhere, so therefore there's no turning forces which are unbalanced. And there's no acceleration. It's not speeding up or speeding down or falling onto the ground. It's completely balanced, and that is equilibrium. So let's just think for a second what would be unbalanced. So if I kicked out one of these blocks on the right hand side here and puffed it away, this whole plank is actually going to rotate round clockwise. And in the same way, if I kicked out the block on the left hand side here, again the whole plank will rotate around anti-clockwise. So in either of those cases, it would rotate and it would no longer be in equilibrium. If we took both blocks away, the whole plank would just fall straight down to the ground, and then there would be an acceleration. Now, although these seem like incredibly obvious things, these are crucial premises to how we're going to solve the two problems going forward.
If you are moving with a force of 200 newton directed perpendicular to a range of 20 centimeters. So for this question, from this question, it is clear that we have the distance, we have the force, and the length, and the distance. The perpendicular distance. So we can cut out the formation equal 200 Newton and R equal to 20 centimeters. And we should convert centimeter to meter. So 0.2 meter. And the degree and the theta is 90 degree. So from the equation, from the top equation, dot R as sin theta. So we just put it 0.2 and cos 400 plus sin theta 80 degree. So the answer is 40 Newton. The calculate the force required to produce 20 Newton meters of at an angle of 50 degree from along 360 meters. So for this solution, we then given the top 20 Newton meters. And the theta 50 degree, 50 degree, and the distance, that means R, 300 centimeters. 300 centimeters to convert meter. Okay, so just like the equation formula. Wait. Okay. Ini we should define the form. At the end of the lever that has a length of 2 meters, if the force is applied directly perpendicular to the lever, then such what is the magnitude of the torque acting the lever. So for this solution, actually torque equal to force over force multiplied by lever. So since we know that amount of force and length of the lever, figuring for us it becomes easy for us. So we just torque equal to 5 Newton multiplied by 2.0. Okay. So we get the answer. For equation number 4, if the same force as equation number 3 is applied at an angle of 30 degrees at the end of the interval, what will be the magnitude of the torque? So from this question, actually that is easy to us because it is easy to us to get the answer because we have angle 30 degree and 2 meter level up then top. So we know the force, the radius and the angle because the force we get from the equation number 3 and the torque. Torque equals to and so we just simplify have to simplify the equation just to the numbers from the equation. That is T equals to F R sin theta. So that from the equation 3 we get conjugate R we get 2 meter and then the delta is 30 degrees. So we calculate, we get log 10 sin 30 and the answer is 5 meter.
So let's look at one of these problems now. In this occasion, Mike is driving his car over a uniform bridge. Now this bridge has two supports, support A on the left hand side and support B on the right hand side. Now the bridge has a mass of 5,000 kilograms and Mike's car has a mass of 1,500 kilograms. Now the bridge is 30 meters long. Now we need to calculate the support provided by end A and by end B of the bridge when Mike and his car are at a distance of 10 meters away from point A. In our answer, we need to include the weight of the bridge and the weight of the car, and we need to include the support forces provided at each end of the bridge. So hopefully you understand that Mike's at a bridge and we need to work out how much force each of these ends are pushing up on. Obviously support A is going to have a little bit more force on it because the car is going to have more of its weight resting on support A than support B just because it's closer. So let's work out how this all balances out. And remember, we've got two crucial premises. The fact that the bridge is staying still means that the torques must balance and the forces must balance. So let's see how we go forward. First thing we need to understand is the formula for torque. We're going to use this an awful lot. Torque equals force times distance. Now our first step then is to draw all the forces we possibly know on this diagram. The first force that we know is the force of the car. Now if we want to calculate the force of the car, we have to know the mass of the car and multiply that by gravity. Luckily we know the mass of the car is 1,500 kgs and gravity is always given to us, so we can work out the force as 14,700 newtons. Next we can calculate the weight force of the bridge. Now this always acts in the exact center of the bridge, or the center of the plank, or whatever you're talking about. But smack bang in the center is where the weight exists. Now this force is given by the mass of the bridge multiplied by gravity. Said the mass of the bridge is 5,000 kgs, so 5,000 multiplied by 9.8 is 49,000 newtons. Now these are the only two downward forces we have, but there are two upward forces as well. The upward force on support A and the upward force on support B. Now that we've drawn all of these forces, our next step is to choose what's called a pivot point. Because we're talking about torques, we need to have a rotation about a single point. Now you just have to pick any point, and usually what I would recommend you do is pick one of the support forces. And actually here we're finding both support forces, but if you're finding support force A, choose the opposite pivot point. So you choose support force B as a pivot point, or vice versa. And that'll become apparent why as we move through this question. Now because we're finding both of them, I'm just going to randomly choose support force B. And I'm going to pretend that all of these forces are causing it to rotate clockwise or anti-clockwise around point B. That's what a pivot point means. The third thing you need to do is know that the torques going clockwise are balanced by the torques going anti-clockwise. And that's because the whole bridge isn't rotating anywhere, so they have to balance. So let's look at that in a bit more depth, because that's where all our calculations are going to come from. And there is one force that pushes the whole bridge clockwise around pivot point B, and that's the force upwards on A. If you had no forces at all coming from these weights, support force A would suddenly be pushing up so hard that it would flip the whole bridge around clockwise. And conversely, if we look at our anti-clockwise torques, the force from the car and the force from the bridge would actually bring the bridge right down, and it would swing down if support force A disappeared. So there are torques, at the moment they're just balanced. So now the torques going anti-clockwise are the torques from the car and the torques from the bridge. And then we have the torque from point A pushing around in a clockwise direction. So the torques pushing around in an anti-clockwise direction from the car and the bridge must balance the torque coming around from support force A. And because we know our torque formula, we can get more specific. The torque of the car comes from the force of the car, its weight, multiplied by its distance away from the support force B. And we know it must be 20 meters because there's a 30-meter long bridge and the car is still 10 meters away from end A. Therefore, it must be 20 meters away from end B, our pivot point. Now we can add this to the torque on the bridge. The force of the bridge, the 49,000 newtons, multiplied by the distance away from the pivot point of the bridge. Now our pivot point is B, so we have to go halfway across the bridge, which is 15 meters, that's half of 30, and that gives us our torque for the bridge. And that all has to equal the force times the distance of support force A. Now we know the distance of support force A, that's 30, but right now we don't know what this upwards force is, so we just leave it as an F. But that's good because we can solve this problem. Putting this whole left-hand side of the anti-clockwise torques into our calculator gives us 1,029,000 equals 30 times the force on A. So now we can just rearrange this, divide this 1 million or so by 30, and that gives us the force on A, which turns out to be 34,300 newtons. So that is our force on point A pointing upwards. Often in an NCEA question, they're only going to ask you to find one of these support forces. So they might just ask you to find support force A. And in that case, because we've found support force A using the pivot point B, I would always recommend using the opposite pivot point to the point you're trying to find. But we're going to carry on with this question, and now it's easier for us to find the force on B. So if we write this into our diagram that the force on A is 34,300 newtons, we can use the equilibrium constant that not only are torques balanced, which is what we've been using, but forces must be balanced as well, which basically mean that forces up must equal forces down because the bridge isn't raising into the air or falling down at all. Therefore, we have a total downward force from the car and the bridge that has to equal the total upward force from support A and support B. So we can now plug all these numbers into this formula and work out our answer. So we have the support force from A here, and that added to the support force B equals the total downward forces from the car and the bridge. So if we add these together and simplify it, that gives us a force on B of 29,400 newtons. And that is our two answers. So we have now found support force A and we have found support force B. And remember, the two concepts we used were initially torques clockwise equal torque anti-clockwise, or torques are balanced overall, and forces are balanced. So the forces up equal the forces down. So let's look at what you need to know from this video. You need to know, first of all, that torque equals force times distance, and torque is a turning force. You also need to know that any stationary object at all is in what's called equilibrium. This means that the forces on this object are balanced, so the forces up equal the forces down, and you're going to need to use this in your formulas, and also the torques balance. So the torques clockwise equal the torques anti-clockwise. You need to know that when you're answering these questions, the first step is to draw all forces. Now most commonly they're going to give you masses and you're going to need to multiply them by gravity to get a force. The second step is you need to choose a pivot point. Now if you're finding the support on one side like support A, then you need to choose point B as your pivot point. The third thing we want to do is do the torques clockwise and the torques anti-clockwise. Now we can work these out using this initial formula of force times distance, and remember, distance is always going to be the distance from your pivot point, not from the end of the bridge. And finally, if you haven't found a complete answer just using torque clockwise equals torque anti-clockwise, you can use the idea that forces are balanced. So the force up equals the force down. So let's look at one more NCEA question. So in an act, Hannah, who's 55 kgs, stands on a seesaw. Now this seesaw has a weight of 210 newtons. Can we calculate the size and the direction of the force that the floor exerts on the right hand end of the seesaw? So that's this part up the right here. Now all distances are shown here in the diagram, and gravity, as usual, is 9.8 meters per second. So let's think what we know. First of all, we always want to draw all forces. So let's see what forces we do know. We know that this force on the left hand side here is pointing upwards. That's the middle of the seesaw. We also know that the floor is pushing upwards, because if it wasn't, the plank would just go straight back down through the floor. And finally, Hannah has a weight force as well. Now it says she has a mass of 55 kgs, but this isn't yet a force. Now this force is going to be figured out by mass times gravity. So we can get Hannah's mass of 55 kgs multiplied by gravity, and we find out that her weight force is 539 newtons. Now we already know that the seesaw's weight force is 210 newtons. So all forces are covered right now. The next thing you need to do is choose a pivot point. Because the question asks us to find the force upwards on the floor, we're going to choose the opposite one, the force on this left hand side, as our pivot point. Next, we have to know that the torques clockwise equal the torques anti-clockwise. So let's look at what those are. Now the torques pushing things round clockwise are Hannah, who's pushing it round this way, round clockwise, and the weight of the seesaw. And that all needs to be balanced by the force on the right that the floor is pushing up on. So again, we get into a bit more detail, changing torque now for force times distance, because torque equals force times distance. So looking at the seesaw, we have a force of 210 newtons, and we multiply that by the distance. And remember, this is always a distance away from the pivot point. So this would be 210, its weight force multiplied by the half a meter. Then we add to it Hannah's torque. Now Hannah is 2 meters away, which is shown up the very top here. And she has a weight force of 539 newtons. Now all of this is going to be balanced by the torque going upwards on the right, the anti-clockwise torque. So here, this is the right hand force multiplied by 3. So that's the force times the distance, because the floor is 3 meters away from the pivot point up here. Plugging this left hand side into a calculator gives us 1183 equals 3 times the force on the right hand side here. So we can just divide both sides by 3, and we end up having a force of the floor of 398.3 newtons. Or if we want to round this properly, 390 newtons. And that is the force that the floor is exerting upwards on this seesaw. Now because we've already found the force of the floor, we have no need to use the fourth step, which is force up equals force down. It would just be if they asked you to find the force on the left hand side as well that you'd need to use this fourth step. But just before we finish, we need to know the size, which we've found, of the force of the floor, but we also need to state the direction. So make sure that you have some kind of sentence somewhere emphasizing that the direction is upwards. So just say that last point. So remember, torque is a turning force, and equilibrium means the torques are balanced and the forces are balanced. And this question here is how you would apply that kind of knowledge to an excellence level NCEA question.
Okay, we are in the last part of torque in equilibrium. So I think we should know the importance of torque in equilibrium in daily life. So torque is an important concept of physics, because that help us understand how things happen around us. With the help of talk, it can be determined what the direction and magnitude of a rotational force apply on a run of object, so allowing us to access the result in many generally talk can help us determine whether the force apply with result in counterclockwise or clockwise motion. Not only that, torque also help us to predict the angular acceleration from which the object rotate. Since torque can be large or small, it is measured in different units such as kilogram meter, gram meter, micro newton meter, mega newton meter, and other than that. Okay, as a conclusion, torque is used in many ways, many aspects of our life, and plays an important role in determining how much force and in which direction is required for carrying out a certain task. Whether we are using a wrench or riding a bicycle or driving a car or any other thing, there are many ways torque is making things happen around us. Actually, we just don't know when torque is happen and how it will be happen. So if we want to convert torque into different unit, we can easily do so by using an online torque converter. It provides a accurate value and a wide range of online torque conversion option to help us with the calculation of torque. Okay, thank you.